This section is about arrays and some basic things that can be done with arrays. In the Wolfram language, an array is a list of lists. This input makes a list using the table function, and this makes an array simply by giving an additional argument to table. The array in this example is 4 copies of a list that contains 5 copies of x. That array can be displayed as a grid using the grid function. To make arrays where the elements are not all just copies of the same thing, the table function can be used with variables. For example, this makes an array of colors using RGB color. The variable r goes from 0 to 1 in steps of 0.2 and specifies the amount of red in each color, and the variable b goes from 0 to 1 in steps of 0.2 and specifies the amount of blue in each color. This makes an array where the elements are numbers. In this example, the value of each element is the row number of that element. And here is a similar array where each element is the column number of that element. This makes an addition table where each element is the sum of its row and column number. Replacing addition with multiplication in that input gives a multiplication table. For arrays where the elements are numbers, you can use ArrayPlot to get an image of the array as a grid of shaded squares with darker squares for larger numbers. For example, here is that same multiplication table displayed using ArrayPlot. The numbers in this array range from 1 to 25. The number 1 in the upper left corner of the grid is shown as a light square, and the number 25 in the lower right corner of the grid is shown as a dark square. Here's an array plot for an array of random integers. The ArrayPlot function can also handle arrays where the elements are colors rather than numbers. This input, for example, makes a plot of an array where the elements of the array are random colors. Digital images are ultimately arrays of elements called pixels. For example, this input gives a tiny black and white image of a letter W. Enlarging that image makes it easier to see the pixels displayed as black or white rectangles. The array of pixel values can be seen using the ImageData function. For this black and white image, each pixel value is either a 0 for black or 1 for white, so this is an array of zeros and ones. If this had been a color image, the color of each pixel would typically be specified by a list of 3 numbers giving the amounts of red, green, and blue in each pixel. This uses ArrayPlot to make a plot of that array of pixel values. The result from ArrayPlot is white on black instead of black on white because the default for ArrayPlot is to make larger values darker, so 0 is white and 1 is black, while in the display of the original image, 0 is black and 1 is white. One easy way to switch the zeros and ones is by subtracting each pixel value from 1, which works because 1 minus 0 is 1 and 1 minus 1 is 0, so subtracting zeros and ones from 1 has the effect of replacing the zeros by ones and the ones by zeros. Arithmetic like this can also be done with entire arrays. This input, for example, subtracts the array of pixel values for the binarized letter W from 1. After switching the zeros and ones, ArrayPlot gives a black W on a white background. That's the end of the examples for this section. To summarize, here is the programming vocabulary from this section. The examples included using an additional argument and table to get a list of lists, using the grid and ArrayPlot functions for displaying arrays, and using the ImageData function to get the array of pixel values for an image. You can find more information about arrays by opening the Wolfram Language and System Documentation Center, clicking the Core Language Instructor button, and choosing Lists from the menu that pops up, which brings up this guide page with links to information on all of the functions that came up in the section, and information on other functions for working with lists. Here are the exercises from the end of this section. As an example, consider exercise 13.5. Make a grid of all possible strings consisting of pairs of letters of the alphabet. The table function can be used with grid to get a grid of all possible pairs from a set of integers. For example, this makes a grid of all possible pairs of the integers up to 10. To get a grid showing letters rather than integers, the FromLetterNumber function can be used to get the corresponding letters. This input, for example, gives the letters at positions 1 and 3 in the English alphabet, and the string_join function can be used to combine that list of letters into a string. Returning to the input that gives a grid of pairs of numbers, inserting string_join and the FromLetterNumber function gives a grid of strings of pairs of letters. Extending the ranges of I and J to 26 gives the grid of all possible strings of pairs of the 26 letters of the English alphabet.